So we'll continue problems on the distributed load. Replace the distributed loading by an equivalent resultant force and specify its location measured from point A. So here, as you can see in the figure, you have a combination of several types of distributed load. So first, in a first step, you have a rectangular distributed load, and then you have a linear load. Okay. So we will divide it like this. First, we will take the rectangular part. For the rectangular part, as usual, the resultant force is equal to the area. So I have here a resultant force replacing the distributed load equal to, in magnitude, to the area of the rectangle, which is 800 times 2. So the force here is 800 times 2. And the point of application, it should pass by the centroid of the rectangle. So it will be at just at the middle. So it will be at 1 meter from A. So the distance from here is 1 meter. Now concerning the linear load here, I can divide it into two parts, one triangle and one rectangle. So concerning first the rectangular load here, you have the height is 200 Newton per meter, and the length here is 3 meters. So I can say that to replace this load, I will put at its center a force. This force will be equal to 200 times 3. So in magnitude, it's 200 times 3. Okay. And the distance from A will be equal to, the distance from here to here is 1.5. I will add to it 2. So 1.5 plus 2 is 3.5. So this is 3.5 meters. And finally, for my triangular load, I know that the area is equal to base times height over 2. So here, this length from here to here is equal to the difference between 800 and 200. Okay, so here this length is 800 minus 200. Then to find the area, I will multiply this height by the length of the base here, which is 3 over 2. In this way, I get the area of the triangle. Now we say that we know that a triangular load has a centroid at 1/3 from the base. Okay, so the point of application of this force should pass by the centroid of the triangle, which is at 1 meter from this base. So from A, it will be at a distance of 2 plus 1 equals to 3 meters. Okay. Once I am done with this step, I have converted my problem from the case of distributed load to 3 concentrated forces. Okay, so as you can see here in the figure, you have 3 concentrated forces, and you know the point of application of each. So now you can easily replace by an equivalent force. First, the first step, you reduce at point A. Okay, to reduce at point A, the resultant force will be the summation of forces. And for the resulting moment, you can select a positive direction for the moment. The clockwise direction is here, because all forces are doing a clockwise moment about A. I will consider the clockwise as positive. So first I have plus 1,600 times 1, plus 900 times 3, and plus 600 times 3.5. Once I find the total moment M resultant about A, I will say that in order to replace by the system by one equivalent force, so what I want to do now, I want to displace the force in a way to have just one single force. In order to know what is the distance d to displace the force, I will just write the equivalency equation, which is that the resulting moment about A should be the same. So, and this is Fr. Okay. So I will just say that Fr times d is equal to the resulting moment about A. Okay. And then I can calculate the value of d. So as you can see, this is we are repeating the same method. And it is always the same method when we deal with distributed load. Okay. Any question on this? Now, here it's something little bit new. Until now, we have seen linear loads. Okay, here we will see a load distributed on an area, but the concept is the same. Okay, so the wind pressure acting on a triangular sign is uniform. Replace this loading by an equivalent resultant force and couple moment at point. So, by analogy between 2 dimension and 3 dimensions, okay, we said that a linear load, the resultant force in a linear load, is equal to the area under the curve. Okay, now in 3D, the only difference is that we have, instead of area, a volume. So we can say that in 3D, okay, the resultant force Fr is equal to the volume under the distributed load. Okay, so here, for example, you have the base of this volume is a triangle and it has a uniform height. Okay, so you can say that here it's equal to, the height is 150 Newton per meter square. You know that when we deal with a force distributed on an area, it's Newton per meter square, or it's Pascal. Okay, it's the unit of a pressure. So it's 150 Newton meter square times, so the unit here is Newton per meter square, or which is equal to Pascal unit, pressure unit, times the area of the base here, which is 1.2 times 1.2, and I will divide over 2 because I have a triangular shape. So times 1.2 times 1.2 over 2. Okay, in this way I have calculated the value of the resulting force. Also, you can think about it in another way. You know that if I have a pressure, how to calculate the force? The force is pressure times area, because here I have constant pressure everywhere on my triangle. Okay, so since it's a constant pressure, I don't have to integrate. It's P times A. So if you do this formula also, you will end up with the same result here, because the pressure is 150 and the area is the area of the triangular base on which the pressure is applied. Now, second step, what is the point of application of the resultant force? So here, also it's similar to analysis in 2D. In 2D, you should have the force passing by the centroid of the area. In 3D, you should have the force passing by the centroid of the volume. Okay, so here, if the force is passing by the centroid of the volume, it should pass by the centroid of the base. Okay, so the centroid G of the base is at 1/3. So from the base. Okay, so this distance should be the base length over 3. So this is, the distance here is 1.2/3. And also in the second direction, it's the same analysis. So the distance here also of the point of application will be also the length of the base over 3. So it's 1.2/3 also. Okay, so now I determined the value of the resultant force. I determined its point of application. Now I will see what they want me to do. They want me to replace the system by one force, one a moment at point O. Okay, so uh, in general we do the inverse. In general, we first reduce at a point, then we find the equivalent force. Okay, here, since we know the location of the equivalent force, we can then deduce the resulting force and couple moment about any point we want. So now what I will say is, if I want to reduce to O, first the resultant force is already calculated, so I can move the force to O. Okay, my force is parallel to x-axis, so this is F resultant. But when I move a force to a point, what should I do? I should add the moment of the force about the point. Okay, so here, who will tell me, is this force doing a moment about x? Is the resultant force doing a moment about x-axis?
No.
No, because it's parallel to it. Is it doing a moment about y-axis?
Yes.
Yes. What this moment is first positive or negative?
About
If I put my four
it's
fingers,
negative.
yes, exactly. If I put my four fingers along the force and the palm of my hand looking towards y-axis, so let me put it in this way. My four fingers like this and my hand looking at y-axis, okay? Then my thumb will point in the negative direction. Okay, so this is a negative moment about y. Now, to find the magnitude of this moment, I know the resultant force. I should multiply by the perpendicular distance. What is the perpendicular distance from the force to y-axis? So this is y-axis here. This is y-axis. Okay. The perpendicular distance will be the following one from here, from this point to y-axis. Okay, you have that the perpendicular distance is equal to, I know that from here to here I have 1 meter. Then from here to the point of application of the force I have 2/3 of 1.2. Since the distance from the base is 1.2 over 3, so this distance will be 2 times 1.2 over 3. And then the distance I should multiply by is 1 plus 2.4 over 3. Okay, so I can say from here that the moment resultant about y-axis passing by O, okay, about y is equal to minus the resulting force Fr, so minus Fr times the distance, which is 1 plus 2.4 over 3. Okay, this is the y component of the moment. Now, for z component, okay, do I have a moment about z? Is my force producing a moment about z here?
Yes.
Yes.
Okay, and is this moment positive or negative?
Negative.
Exactly, negative, because if I do the right hand rule, I put now my four fingers parallel to the force and the palm of my hand facing z. So if I put my hand like this, my thumb will point downward. So this is a negative moment, and I should multiply the force by which distance? What is the distance between my force and z axis? Look at the figure. I should take the perpendicular distance to the force, okay, and to the axis. So it is this distance from here to Z, okay. The distance from the force to Z is 1.2 over 3 plus here I have a small thickness of 0.1, okay. So I can say that the resulting moment about Z is equal also to a negative value, so it's minus Fr times, now the distance is 1.2 over 3 plus 0.1, okay. And in this way, I have found the component of my moment. Of course, along x, no component, since the force is parallel to x. So now, since I know the component of the moment, I can find its resultant, okay? And I can find its direction also if I want. Because if I want to draw it on my figure, the vector moment will have a negative y, negative z component. So it will be, if this is yz plane, so this is z, okay? Then my moment vector will have negative z, negative y component. So this is my resulting moment, let's say, okay? And I can find the angle here by just doing tangent minus 1 of frz over fr1. Okay, so let us look together at the solution briefly. If you want also another method, هن they did the vectorial method, okay? You can also do it here, because in 3D we said that or we can do the method of right-hand rule, or also we can do the vectorial method because it is easier than doing the right-hand rule. So if you want to find the moment about O, what can we do if you want to do the vectorial method? If I go back to my figure, okay, we said that the point of application of the force is known. It's here. Let's call it G. Okay. Then simply I can just say that the resulting moment is OG because I want the moment about O. So I can just do OG vectorial FR, as simple as that. Okay. So this is why I tell you in 3D sometimes the easiest way is to do the vectorial formulation. Okay, now just I need coordinates, and already I found for G the location of G, so I need coordinates of G. First, for point G, it is in plane x, y, z, so no x component. Okay, and I have already found that this distance from y-axis, I know it, it's equal to 1 plus 2 times 1.2 over 3. So for the coordinates of G, it is 0. Along Y, it is 1 plus 2.4 over 3. And so it has a positive component along Y, and along Z, it has a negative component. And the negative component of it is minus 0.1 minus 1.2 over 3. So minus 0.1 minus 1.2 over 3. Once I find the coordinates of point G, then I know my vector OG, okay? So all I have to do is to say that the resulting moment, the resultant about O vector, is equal to OG vectorial FR. Of course, all of them are vectors. Now I replace OG by its value. So I have 0i plus along J I have 1 plus 2.4. So here, if you want, let us calculate it. 2.4 over 3 is 0.8, and plus 1 is 1.8. So it is 1.8 along G. And along Z, okay, along Z I have 1.2 over 3, which is 0.8, and 0.1, so, and it's negative, so it's minus 0.9. Minus 0.9 along K. Okay, vectorial, the value of my force. So here, as I perform the calculation, it's 108. So vectorial on 108 minus 108i. Why minus? Because the force is in the negative x direction. So vectorial minus 108i. And now, look, it's much easier than doing the vectorial method, the right-hand rule method. I just do the expansion. I have g vectorial I. What is g vectorial I? Plus or minus?
Minus.
It's minus k. Okay. So I have. Okay, look, just 1 minute. I should have a negative. I should have a negative result for the moment. So let us check what's the issue. OG. So it's 1.8. We should have a negative moment about z. So let us see what is the error here. We have that vector OG has positive. It's negative y. Okay, this is look. This is the error. The error here is that here when putting the coordinates, we switched them. Okay. No one paid attention for this. Look, so you see how you can find your errors here. If you do 1.8 vectorial minus 100 I, you will get a negative. You will get a positive component along k. But if you do the right hand rule for verification, you know that the moment is negative. So you can see that something is wrong. So the mistake we did is that we switched here the coordinates. Just that's it. So here, this is z and this is y. Okay, so we should switch them. So just I will do here like this. So here it should be switched. Okay, so vector OG here will be 1.8k. Okay, so instead of j here it's k minus 0.9 j, and now it will work. Okay, so when you do k vectorial I is plus j, and already you have a minus, so we'll get a negative moment along y as expected. So it's minus 1.8 times 108, and this is along j. Okay, and now j vectorial I is negative, it's minus k, and minus minus already is plus. Okay, so I have minus 0.9 times 108 along k. So try always to verify if your results are right or not. So even if you do the vectorial method, you can just verify from right hand rule your signs. So if you have an error, you can find. Okay. Any question on this problem? Why we did write FR as minus 108, because if you calculate the value of it, first the magnitude is 150 times 1.2 times 1.2 over 2. If you do the calculation, it's 108. And since it is parallel to x in negative direction, then it is minus 108. Okay. Any other question? So here, as you can see, when performing the calculation, you get a negative j component and negative k component. Okay? No. So let us start with something else. The beam is subjected to the distributed loading. Determine the length B of the uniform load and its position on the beam such that the resultant force and coupled moment acting on the beam are zero. Okay, so here we have a distributed load acting on the beam, and we want to replace it by just a resultant force. Okay, so first we have a rectangular load and a triangular load. Then, as usual, okay, here there is a little bit different given. So here A and B are unknown, and we want to find the relation between A and B. So what should be A and B in order to have a resultant force and couple acting on the beam equals to zero. So first we will express our resulting force and resulting moment function of A and B, and then we will replace we will put the condition that the resultant force is zero and the resultant moment is zero. Okay? So to start with, I have a rectangular load here. So when I have a rectangular load, the resultant force applied should be equal in magnitude to 40 times B. So the magnitude here is 40 times B. And the location is, this is the point of application. So the distance from here to here is A plus B over 2. So it is A plus B over 2, this distance. Now, concerning the second force, okay, since it is applied from downward side, okay, it's a positive force upward. So in magnitude, it's equal to 600 times 6 over 2. And concerning the point of application, it is at 1/3 from the base. So this distance here is 10 plus 1/3 of 6, which is 10 plus 6 over 3. So it's equal to 12. Okay, now once I reduced my system, I will write the expression of the resultant force and the resultant moment. So first, F resultant is equal to minus 40B, which is the rectangular load, and plus the triangular load is 30 times 6, okay, which is 180. So plus 180, okay, equals to 0. So from this condition that the resultant force is 0, I can find the value of B. So I deduce that B is 4.5. Okay, so B equals to 4.5. Now, the second condition to find A is to use the condition that the resulting moment is 0. So if the resulting moment is 0, then it will be 0 about any point. So you can choose any point on your beam. So let us select the origin. So we will do, if this is O, okay, let's call this point O. Then we will say that the resulting moment about O is 0. So MR O equals to 0. Then this equation will give us, first, let us choose a positive direction. So if we select the counterclockwise as positive, okay, you have the rectangular load is doing a clockwise moment, so it's minus. So it's minus 40 times B times this distance, which is A plus B over 2. So it is minus 40B times A plus B over 2. And concerning the moment of the triangular load, the triangular load is doing a clockwise moment, so it's positive. So plus the value of the load, which is 180, times the distance from O, which is 12, times 12. So since you have already calculated B from the first equation, you replace B by its value here, then you will end up with one equation with one unknown. Your unknown in this equation is A. You can calculate then the value of A. Okay? So in this way, we have calculated what should be A and B in order to have a resulting force and resulting moment couple equal to 0. Any question on this problem? Okay. So now, okay, guys, just concerning, before I was used to give integration, but I know it's a little bit complex for you, so I will, you are not responsible of this, okay? So you don't do anything related to integration. So this problem, don't cover it, okay? So you can stop there, I think. Let me check if we can do anything else. Okay. So just all problems involving integration, don't do that. So this one also, when you have a variable distributed load, you are not responsible at all. Okay. So let's do this one. Replace the loading by an equivalent resultant force and couple moment at point B. So here we have a system of distributed loads acting on our structure, okay? And we want to reduce the system to point B. So first, as usual, we start to replace each load by a force and determine its this point of application. So first, for the rectangular load here, I can replace it by a force at the center here. So the value of it is equal to the area, which is 50 times 4. And the point of application is just at the middle. So this distance here is 2 feet. So this distance is 2. Now, concerning the second distributed load, also as usual, I divided into a rectangular and triangular load. Okay. So here I have a force just at the middle for the rectangular load equals to 50 times 6, which is 300. And it is just, you should know, it's here, what is a little bit new in this problem. So you have a little bit, you have an inclination. So since this force is perpendicular to the beam here, and the beam is doing 60 degrees with the horizontal, then you can deduce that this force will do an angle of, so if I do the expansion here, okay, the angle here with the horizontal will be 30, okay? So this is 30 degrees. So if I want to decompose this force after, I can say it's doing 30 degrees with horizontal, or I can say it's doing 60 degrees with the vertical, okay? Now, concerning the
Doctor,
triangle, yes?
how did we know that it was doing 30 degrees? Can you please repeat?
Yes, of course. So Marissa, you have this force is perpendicular to the beam, okay? Because it's perpendicular to the beam, this angle here is 90 degrees. Then, if I do the extension of the line of the force, this is 90, this is 60. What will be the angle here?
90 minus 60, okay.
Yes, it will be 30, okay?
Thank you.
Now, concerning the triangular load, okay, for the triangular load, I have to calculate the area, okay? So here, the thickness here is just 100 minus 50. Okay, so this is 50. 50 times 6 over 2. Okay, so it is 150. Okay, so the force will be equal to 150. And concerning the point of application, it is at 1/3 from the base. So this